Okay, class. This video is going to involve in my PowerPoints the blood vessel formulas that I have. This is a newly designed PowerPoint file. So where we are is to try to understand about blood vessels and even in respiratory. So this is going to really explain mathematics, shall we say, of fluids and gases. Fluids and gases in a pipe and so forth. The way I have this set up is this is going to be kind of my scratch paper if I need some. My scratch paper. So I may do a little something here. It just depends to see how this goes there. Now, you may not understand everything about it, but at least it'll give you an idea as to what this is about when we say you have high blood pressure, hypertension, and so forth. All right, so let's see what we got here now. All right, the mathematical analysis of the circulatory system. I've taken 9 things I think of interest. Now, this is not really in your textbook, so some of it might be, but very little of this is. But this will be kind of explained. Okay, we want to talk about pressure. We want to talk about something called mean circulatory filling pressure, which is not in your textbook. We want to talk about flow, resistance, peripheral resistance, things of this nature there. Okay, so you have this here. All right. We start first with what really is pressure. What mathematically is pressure? I'm going to say you have to have 3 components present to have pressure. Some pulling or pushing force. You need a force like gravity or something. Some force. In this case, since this is gas as a liquid, then I'm going to say the volume of the gas of the liquid. And then the density of the gas or liquid. Density is how many particles per some unit volume. How many particles per some unit volume. The more particles per some unit volume, the more dense something is. I'm going to say that pressure equals volume times density, in green, times the force. Okay? And pressure, so if you do this mathematically, volume over 1 times particles and so forth, everything would cancel out. Volume would cancel with this. Particles would cancel with this. So what would be left is force, which is the pressure. Now, when you take your blood pressure, for example, we use a mercury sphygmomanometer. Even the barometers a lot of times are mercury. Why? Because if you use water, it would take too much water, too much volume of water. You couldn't even, if your blood pressure was 120 over 80, it would take a water height up almost through the ceiling. Since mercury is 13.6 times more dense than water, we can do a lot more with a smaller volume of mercury. So pressure is a force, really. Pressure is a force. And this is how it would be calculated. It's a force. Okay. Now I come to this next one. I'm going to call the mean circulatory filling pressure. Okay, now this is what I want you to think of. You have in your body the heart, and then you have the blood vessels connected to it. You have the heart and the blood vessels connected to it. The heart is a pump, it's a compression unit. But even without the heart, you would still have some pressure in the pipes. Think of a water hose. If you unhook the water, if you kept water in the hose, kept both ends of your hose, took it off the outside water faucet and kept both ends, there would still be pressure inside the hose with that water in it, even though you aren't pushing water out of your faucet. So think of that. So the mean circulatory filling pressure is the pressure in your blood vessels if you didn't have a heart. It would just be the pressure of the vessels themselves. What would that pressure depend on? It would depend on the volume of blood in your blood vessels and the amount of vasodilation or constriction of the pipe. Because think about it, I took the water hose pipe off the faucet, closed both ends, and squeezed down on the hose. The pressure would go up. The pressure. So vasoconstriction increases the pressure. Dilation decreases. Let's take another one. I'd let some of the water out of the water hose on one end of the cap. The pressure would go down just because I decreased the volume. Now, the average mean circulatory filling pressure in your body is about 7 millimeters of mercury pressure. If you recall, the average blood volume is about 4 to 6 liters with a median value of 5. So with a median value of 5, you have about 7 millimeters of mercury pressure with average blood vessel diameter. All right? Okay. So here's an example of this here. Okay, so now we want to talk about under mean circulatory filling pressure, unstressed and stressed blood volume. Unstressed and stressed blood volume. Okay. Let's say that I took a person and could drain all the blood from their body. And then stop the heart from working. So the heart would stop working. I drain all the blood from their body. I don't hook the heart back. Okay, but I start putting blood back in the body. Okay. So when I start putting blood back in the body, I put the first liter of blood back. The first liter. When I put the first liter of blood back, the pipes are all collapsed. So I measure the pressure and it's pretty much almost zero. Not much. I put the second liter back. Now I'm putting 5. I measured the pipe still is not stretched. So that means I haven't stressed the walls of the pipe. See right here? Put the second. So that would be unstressed. And I also don't get much, probably get close to 0, maybe a little more. Put the third liter back. The third liter now is enough to start slightly stretching the walls. So now I start to get more of a stressed volume because now I'm stressing the wall by putting it in. They're not as collapsed. Let's say I get a 3 or 4. Then I put that fourth liter back. Then I start getting even more. Now, see right here, I'm in the stressed blood because I'm pushing the pipe out. So other words, what I'm saying is that as I put it back, I start getting more. So the average mean circulatory filling pressure is around a 7. So that volume, I'll go over here. Heart's not working, let's say. Don't have a heart. Take that out. So this unstressed volume would come up to, let's say, around 3. Then I'd start stretching the walls of the pipe out, and that would be that stressed volume. So anything over around that 3 or 3.5 would then be stressed because I'm pushing the walls of the pipe out. And that's what I'm going to call stressed and unstressed. Unstressed blood volume is a volume before there's enough to stretch out the blood vessel walls. Okay, so that's what we'll say there. All right. Now I'm going to come in and I'm going to add the heart. Now before, remember, this mean circulatory filling pressure, we said, this mean circulatory was without a heart. We got up to a 7, let's say. We could get up to a 14. If we came in, put as much blood as we could in the pipe and kind of vasoconstricted, we could get up to possibly around a 14. 12 to 14. Now, I'm now coming in to the pressure total. See, prior to this, the pressure total in your blood vessels would have been the MCFP, the mean circulatory filling pressure, because I didn't have a heart in there. So I'm saying when I add a heart, the pressure total in your pipes would be the pressure of your compression unit, which is the heart, and that mean circulatory filling pressure, which is just the vessels by themselves with the blood and that. Now, the key to this is, in order to stand up, you need a 60 millimeter pressure. Why is that? Because when you're lying down, your brain and heart are on the same level of gravity. Your brain and heart. But when you stand up, your heart is going to have to compress a little harder to push blood against gravity to go to your head. So the average person needs about a 60 millimeter pressure, a mean arterial pressure of 60, we haven't talked about it, but a mean arterial pressure of 60 to stand up. If the most you could get is 12 to 14 by just the blood vessels alone, what does that automatically mean? You cannot make it without a working heart. You cannot make it without a working heart, because you got to go to at least about a 60, and the max you could get with the mean circulatory filling pressure would be a 12 to 14, and that's with everything going. Okay? Now, I'm going to use this one. I'm going to say, assume this container, that whole container, are just your blood vessels. So this would be your mean circulatory filling pressure. Here's the heart, though. We're adding that. All right? The pressure in this container is the mean circulatory filling pressure. It has an average of 7, but can raise or lower, as we said, because of adding more fluid or squeezing down the tank. When you add the pressure of the heart, it would be the mean circulatory filling pressure plus the heart compression pressure. I hopefully can get a 60 and much greater than a 60. So I'm showing you that the heart that compression unit is very important, because you need that. So you could not make it without a working heart. Okay? All right, we go further now. Now we're getting to talking about flow. We're getting now to talking about flow. So now I'm going to do another video in a moment to talk further about this. Okay?